For this week, the overarching idea was the polarization of conductors and insulators. So, conductors are materials that have mobile charges, while insulators are materials that do not have mobile charges. And it's important to note that electrons are not necessarily always the mobile charges in conductors. And based on the idea of conservation of charge, charges cannot be created nor destroyed, and therefore the total charge on an object can only be changed by transfer of charges to or from that object. The videos then went into how different insulators and conductors can become charged. So there are three main ways. The first one is charging by contact. So this is when charges are transferred between objects that are in physical contact with each other. And our lab with invisible tape is a good example of this. And so when charge is transferred onto insulators, the charges cannot move around readily, and thus they do not move around to different locations on the objects. Whereas on conductors, the charges do not stay in the spot where the contact was made, and they rearrange rapidly. For polarization in an insulator, the charges in an insulator shift when polarized by an external electric field, but there are no mobile charges that can actually move large distances. Eventually, if the electric field on an insulator is steady, the insulator will have a steady non-zero dipole moment P. For the polarization of conductors, the charges are mobile and do move long distances when exposed to an external electric field. And then an example is in an ionic solution, which is a conductor. The solution will eventually reach equilibrium and have a well-defined electric dipole vector. And in a metal, which is a conductor as well, the electrons themselves are mobile, but the protons remain fixed. And in the equilibrium position of metals, it's similar to the equilibrium position that was reached in the ionic solution. And in equilibrium of a conductor, all the excess charges will lie on the surface of the conductor. And additionally, in this equilibrium position, the net electric field inside the conductor is zero. We then talked about, in the videos, they then talked about symmetry. So if an object like a block of metal or something else that's a conductor is symmetrical, then the surface charge distribution will exhibit the same symmetry as that object. And then we then talked about charging a conductor by induction. So the example were two metal spheres that were in contact. They were initially neutral. They were then exposed to a positively charged rod. The sphere closest to the rod became negatively charged, and the sphere farthest away from the rod became positively charged. The spheres were then separated, but the rod was still there, but then the rod was removed, and the spheres were still positively and negatively charged respectively, meaning that it is possible to charge without contact through induction. And then we were finally given an example problem that showed how to calculate the electric field inside a polarized metal block. What I learned that I already knew was that conductors and insulators are, and I also knew that the charges in insulators can't move while they can move in conductors. And in chemistry, we learned about how charges move in ionic solutions specifically. What I learned that I didn't know was that how insulators are polarized. That was especially new to me. But I also learned in more detail how both insulators and conductors in general become charged. And I had also never learned about the symmetry of charges or the equilibrium of polarized materials before. What sparked my curiosity was the idea that objects can be charged even without physical contact, and that's really interesting because it seems like it can open up a lot of doors to cool applications and technologies, and you can do a lot of cool stuff and experiments using that property. Relating this to my major, which is aerospace, is difficult, but material choice is very important in plane design, and it could relate because if you choose a conductor when you need an insulator, or vice versa, and the material choice is wrong, the materials could become charged or charged in a way that you do not want them to, and this could affect the material characteristics and interfere with the flight and potentially be a safety problem. A topic that was most difficult for me was the idea of the electric fields inside the materials, especially the idea of the electric dipole vector of many vectors, of many dipoles inside of insulators. And I followed up to the videos by reading the textbook. That's a great supplemental resource that helped me to obtain a greater understanding of the material. And especially sections 14.5, 14.6, and 14.7 were great follow-ups to help strengthen my understanding of the material. Thanks for watching.